Hello, as you may have noticed, switch from Paint. I wanted to keep stuff minimalist as much as possible, but I got fed up with the pixelated looks of curves on Paint, so yeah, I switched. So now, essentially, we have this problem for today. However, the nuance is I'm gonna rederive it after solving it because I think that we're going to spoon-fed the solution. I did not rederive it like entirely. There's a problem that I got stuck in, but let's go ahead and continue anyways. So we have a continuously differentiable closed curve on the interval from a to b, the parameter I mean, and it's never equal to 0. And we have index defined through this, and we have to prove that it's always an integer, and we're given a hint that basically makes it really trivial. So what we do is we just find a function like this, phi such that phi prime is equal to gamma prime over gamma, which is done through integration, which you can do on this particular function, gamma prime over gamma, and then you can just offset it so that phi of a is equal to 0, which that's not a trouble. Now what we have to do is we have to prove that gamma times e to the power of negative phi is going to be constant, which is fairly simple. What we can do is just differentiate it, because phi is differentiable, e to the power of minus x is differentiable, gamma is differentiable, so it's not a trouble. We just do it the regular way, plus gamma times negative phi prime times e to the power of negative phi, yeah? And when it comes to phi prime, it's gamma prime over gamma, so this over here becomes minus gamma prime, so this stuff cancels out and becomes 0. Alright, so this was fairly simple. Now, with this in mind, we can derive more stuff. Reading suggests that at the beginning and the end, e to the power of phi of a or b is going to be 1. Basically, this comes from the fact that phi of a is equal to 0. Therefore, e to the power of phi of a is equal to 1. And now the nuance here is that gamma a is equal to gamma b, which directly influences the value of e to the power of phi of b, since this thing is constant. So what we get here is essentially e to the power of minus phi of a is equal to e to the power of minus phi of b. And since this is equal to 1, from this stems the fact that just e to the power of phi of b is also going to be equal to 1. Alright, so now using these facts, I can finally go ahead and show that this interval is going to be an integer, which is actually fairly simple. So what we can do is we can say that this is just phi prime, so when we do integrate it, we just get phi of b minus phi of a. And now recall how phi of a is 0, so that's going to be phi of b over 2 pi I. Now again, recall how e to the power of phi of b is equal to 1. This implies that phi of b is equal to 2 times pi times I times n, where n is an integer. And now coming back here, this is gonna be just n, where n belongs to the integers. Alright, so now the part that I was talking about, how to derive this, because, well, essentially what this does is when we take the complex plane with the 0 point here, and let's say that we have a curve here, the amount of turns that it does about this point 0 is going to be the so-called index or Winning number. So how do we come here? Well, first of all, essentially my idea behind this is let's express gamma of t as a product of some r of t. Okay, that kind of looks like gamma. Let's rewrite that. R of t times e to the power of I theta of t. Now I'm gonna do an assumption here that r prime of t and theta prime of t exist, aka they're differentiable. Because I really can't prove the contrary, unfortunately. But given this assumption, I can come to the original integral, how people likely got it, essentially. So when we differentiate this, what we get is gamma prime of t is equal to... Okay, actually, let's not write the argument for the sake of simplicity. So what we get is r prime times e to the power of I theta t. Okay, I just said to not write the argument and then proceed to do that. I'm so silly. Plus, we get here is I times theta prime times r times e to the power of I theta. Now what I'm gonna do is I'm gonna bring out the r here. Let's say that gamma prime is equal to essentially 1, okay, no, r e times I e to the power of I theta, okay, and inside what we get is r prime over r plus here we have this thing already, so we don't need to divide anything. So what we have left is I times theta prime. Now this is just gamma, so when we attempt to perform a division, what we get is gamma prime over gamma is going to be equal to r prime over r plus I prime theta. Now the thing is, what we want to find about the data is, first of all, it's not a pure argument function, because I want it to be differentiable, recall that. So whenever we do a full circle, it doesn't snap back to 0, it continues going to pi plus some other thing, so that's important to note. And what I need to find is essentially the endpoint theta b minus theta a, which is conveniently given when we integrate this thing. So let's go ahead and try to integrate the left hand side and the right hand side. Get the integral of from a to b of gamma prime over gamma dt minus the integral from a to b of r prime over r dt is equal to I times theta of b minus the theta of a. Yeah? Now you may already see why we're dividing by I and 2 pi, because here we get stuff in raw radians. So again, let's insert a new page, continue here. This integral we don't really care about because we have it in the definition. To care about is this integral, and what we can do is essentially just say that we have r prime times g of r, and g is g of x is equal to 1 of x, so this is just we can apply reverse chain rule. Now the reason I denoted this weird way is because I took the problem from Blue Reading's textbook, and the substitution you'll love and know is phrased here in a way that makes it impossible to apply when the substitution you use is not a monotonically increasing function. So it makes sense to do it this way here. So yeah, now that we express it as from a to b of g of r times r, okay, that was horrible, r prime dt, we can rewrite it as integral from g of a, okay, no, not g of a, I'm stupid, from r of a to r of b of essentially 1 over rt dt. Now thing is, rb is equal to ra because the curve is closed, so this thing is going to be equal to 0. Alright, and yeah, that's about it. That's how we come here. Now as for the differentiability of these things, essentially the way I go about it is, well, what we do first is we go ahead and define gamma in a different way instead. We define it as sum of two functions, a of t plus I times b of t. Now, if gamma is differentiable, then so are a of t and b of t. And what we can do next is we can say that, well, r of t is equal to the square root of a squared of t plus b squared of t. And we can bring it out and say that, well, we multiply r of t, and inside we have a of t plus I b of t over r of t. So under this definition we already have r of t as differentiable. Now the question is about data here, and what we get essentially is that e to the power of I theta of t can be rewritten in this new definition as a of t plus I times b of t over r of t. Now the issue still comes with showing that theta of t is differentiable, because if e to the power of I theta t is differentiable, that does not necessarily mean that this theta of t is also going to be differentiable. And again, there are some ways to go about this, but there are still a lot of issues to deal with here, so I would just omit that, and let's say that this was basically just the formulation ground for the integral, and the differentiability here is just a nice thing for specific curves, but we don't really care about it because in the final equation that we've got here, we don't really involve derivatives of some self-defined functions. That's an unfortunate outcome. I may make another video on this if I find a way to deal with this issue over here. But yeah, that's it for today. So bye.